Hello, thank you very much for joining us. I'm Andy Nari. I've got Michael Dearman here as well as our CEO.
Hello.
So this is just a basic introduction and training into the Quarch product range and how it relates especially to PCIe SSD testing. So Quarch technology, we were founded in 2006. So we've had a lot of time and experience in the market. The company was founded for the purposes of assisting storage companies in testing hot plug and fault injection at a time where this process was a very manual thing to do. It was complex, took a lot of effort, and the company believed we could do better. So we now support almost every major storage vendor. These are the drive manufacturers, they are silicon controller designers, they're the storage array, from old SAS systems to the latest all-flash arrays. We also support the networking, telecoms industry, and even things like automated vehicles. Basically anywhere that people are throwing around large amounts of critical data, and we need to be very certain that the hot swappable and removable parts of the system are functional and sound. We support almost every major interface. So for many of you, that will be U.2 and slot-based AIC systems, but we do M.2, U.3, the latest EDSFF systems. We also support networking interfaces such as SFP28 and older interfaces like RJ45 and USB. Basically, any removable part of the system, we can instrument. We support the latest protocols and speeds. For most of you, again, that's going to be Gen3 and Gen4 PCIe. And we'll also have Gen 5 coming out in Q1 of next year. Quarch is really the industry standard for hot plug and fault injection at the physical layer. We're recognized across the industry. As I said, we're used by almost every major storage vendor, especially in the US. We're a mandatory part of hot plug testing for the NVME promoters group. So anyone that's taken a drive to one of the University of New Hampshire's interoperability lab plug fests will have to have passed the Quarch hot plug tests in order to show that they meet the standard. So we've got two major product lines to look at. The first on the top are our hot plug and physical layer fault injection units, also known as breakers. These are small interposers. In this case, that you can see the example is clipped behind a standard 2.5-inch drive. The drive can then slide into the enclosure as normal. And with this module, we can automate hot plug and a wide range of physical layer faults. So it's a very simple thing to put in place, but it can automate a very wide range of tests. Second line, we'll look at our programmable power modules. This is a bit of a different solution. In our first product, we can cut power to a drive, but that's all. With this system, we can do everything from margining, ramping, glitching, sudden power loss, and also comprehensive power analysis in terms of power usage in all sorts of different workload scenarios. So really, this second product can replace an oscilloscope, 2 current probes, and a dual channel power supply all in one unit that is much easier to use and can provide an order of magnitude more data. So first of all, why test hot swap? The main thing here is that you have a removable part of the system. If you're pulling something out or plugging it back in at an unexpected time, there are lots of potential problems. Hot swap operations can lead to memory corruptions, data loss, blue screens of death, unexpected reboots, the sort of thing that you absolutely cannot afford to have in an enterprise storage system.
It's particularly difficult with PCI Express as well. The enterprise storage comes from a background of SAS and SATA, where you had simply power and data. You didn't have many sidebands. Whereas PCI Express comes from a world where the intention was that it would, I know hot plugging was in the original specification, but very few vendors ever implemented it. And so we're taking a protocol which was intended for a very static world of adding cards in motherboards that is now being applied to external interfaces and cabling and places that have been quite a big challenge. And the addition of all the sidebands in terms of ref, clock, wake, burst signals and those timing dependencies means that we see a lot more issues with PCIe than we did in a SAS world, for example. And we found plenty of issues in SAS in a way. So it's challenging, and it requires a step up in terms of the way you look at testing to make sure you cover all those corner cases.
So the architecture of the modules is really quite simple. Between the host and the device, we put our Quarch interposer module. We have individual switches on every critical pin of the connector, and we can control that from one of our external control units.
So those switches are appropriate to the signal which they're switching. So where we have a power rail, we will use high power FETs so that we have very little voltage drop, and we can deal with the high currents that are required. Where it's data, we use RF switches, which are typically bilateral and typically passive, so we're not retiming or adding latency to the signal. And where it's a sideband signal, we'll use something appropriate to that sideband signal. So we switch SM bus, which is a wired OR bus, a bidirectional bus. We switch first slightly differently because it's driven from one side. It depends on the sideband, but in each case, we apply a switch and technology which is appropriate to that signal.
And as Mike said, as passive as possible. Mm-hmm. So the idea here is that by default, all the switches are closed when you first attach the module, which means the host and the device are directly connected to each other, no redriving, no retiming. Our module is completely invisible to the system, and your devices will be running as normal until the point you then choose to activate a hot swap or fault injection point. So start basically with the simple sequencing of a hot plug. On the top left there, we can see just a standard connector shape. We've got long and short pins. So when you plug an SFF drive into the slot, the pins do not all meet at the same time. There are 3 different lengths of pins, and they will meet at slightly different times as you push that in. In a very standard smooth scenario, that will be roughly 25 milliseconds between each length of pins. Now in the image on the right-hand side there, we've created a simple timing scenario to show this with 3 different timing sets on the red, orange, and green traces. And what we can do with these modules is that we can connect the different lengths of pins at different times to simulate fast versus slow hot plugs. So we can simulate, as we would by default, a smooth, steady hot plug by a careful engineer. We can also simulate someone slamming a drive into the enclosure as fast as it's physically possible to do. Or a case where a drive is plugged almost all the way in and then left for a couple of seconds and then click the last bit of away. So we make it very easy to test all the different corner cases that could occur, and we also make it entirely repeatable. So if you find a scenario where there's a failure, you can repeat it again and again until your R&D team can narrow down what the problem is and find a solution for it. Previously, this kind of testing would involve engineers sitting at a rack performing hundreds of hot plugs manually, trying to work out what was going on in the occasional failure, but that's very inefficient and it takes a lot of time. And there's a significant risk that you miss things entirely that might not be visible until you have 100,000 units in the field. As well as just a simple connection, we can also simulate the mechanical pin bounce. So connectors do not always connect perfectly. Sometimes the pins will scrape and bounce over each other as they're plugged in. And in the case of the green trace, you can see that we have connected and disconnected twice before the permanent connection's in place. So we can create these pin bounce scenarios in different pins. For instance, what happens if a reset or interface detect pin is bounced on connection? There's a possibility that your state machine will take that as an instruction and go down a completely different path that you would never have considered before. So again, it's important to check all the potential problems are covered, and we can make this very simple. The next thing we can look at is fault injection. Now, the basic hot plug scenarios are useful for a very wide range of tests. They're also useful for automating cases where otherwise the test would have to stop and wait for user interaction to pull or plug a drive. But there's a huge range of other things that can go wrong in a storage system. For instance, what happens if you plug in a drive that has a broken pin on the connector? What happens if there is damage to a connector or drive during normal operation while you're running data? Now, you can create these tests manually, but it's complex and difficult to do, will not often involve physically damaging the system in order to create them. We can create these faults with a couple of commands in a matter of seconds, and you can automate hundreds of them in a sequence to run overnight. And in every case, we're looking to ensure that either the device is detected as bad and shuts down correctly, or the appropriate warnings or dual redundant failure mechanisms take place correctly.
So if I have a dual ported drive and I want to test the failover from primary to the reserve port, then how would I do that normally? I might have some cables I would manually pull out of the drive. I might have some command, but these are difficult to instrument, and these are not repeatable scenarios, or not necessarily using the same code paths anyway. where we have the module in place. If I wanted to do a failover from the primary port to the secondary port, it's a single command. It's simply turn off the switches on the primary port, that port goes away, and now you can see how your system responds. And the response you're seeing is real. So we haven't told the software to nicely shut down the primary port, we've just cut it away. And it doesn't have to be the whole port. We can cut off the receive pair, we can cut off one side of the receive pair, or any of the sideband signals. So we have huge control over the faults that we can inject into the system. Similarly, with power interruptions, it's a single command, bring power down, bring it back up again. So far easier than cutting wires and soldering onto boards and interfering with physical hardware.
And of course, all these failures are highly likely to occur at some time. All it takes is one broken pin in a connector or something that is a track that's slightly damaged during manufacturing, and these failures will occur in real operation. The next thing we can do is, rather than simply opening and closing the switches for a long period of time, we can eject very precise glitches. So we can select one or any group of switches. On the RF switches, the minimum time is around 50 nanoseconds. And we can open and close the switches for that precise length of time. So we can create a single glitch, for instance, and at 50 nanoseconds, that would rack up a few physical error counters, but it's probably going to do nothing else. We can repeat glitches in a nice steady interval, or we can use a random repeating glitch using a PRBS generator, which will create something that looks very similar to cases where you have a damaged connector and vibration in your system and you have random errors occurring.
Yeah, so the idea behind the PRBS is to simulate a bad link. And the bad link doesn't have interruptions at nicely spaced intervals. So what we do is you might see you see bursts of errors occurring, and that's what the PRBS generator is attempting to simulate is bursts of errors appearing on the system.
And of course, at small glitches and limited PRBS ratios, again, you're going to see error counters, but very little effect on the system. However, as you increase either the glitch length or the ratio, then you're going to get larger numbers of errors until you get to the point that you'll see performance drops in the system, and eventually we imagine the port will be marked as bad and shut down. But the important thing to ask in this case is, at every level of fault injection, does the system make the correct choice? Do you fill the port at the right time? Do you shut down the drive at the right time? Are there cases where data corruption actually occurs, or the significant performance drop before the device is detected as bad and shut down? So signal driving is another feature that we added to our latest generation of drive modules. So all the previous examples we've given are where we can open and close a switch to isolate the host of the device. However, some of the sideband signals can now be actively driven. So this allows us to take things like burst, wake, dual port enable, and force them into a high or low state. Now, the driving options that are available depends, again, on the electrical spec of the interface. So some signals, for instance, can be either driven or left to float. Sometimes they can only be driven on one side. However, this lets us do a useful number of other things. For instance, we can force dual port enable to force the drive into a particular state. We can glitch burst to create a reset of a very specific length, for instance, to ensure that your drive will respond correctly to all of the allowable lengths of the burst reset. We can link the driving feature both into the pin bounce and the glitch feature. So we can drive for a very specific length of time, or we can force high-low transitions using the pin bounce patterns. So here's a very simple example setup. So the Quarch Turden system is modular. So it's very easy to start out with and evaluate, and then scale up as necessary. So here we've got a Quarch module between the host and drive. That's then cabled out to one of our interface kits, which is then controlled by TestPC. So in this example here, we've got one of our PCIe SFF modules behind the drive. And in the video, I'm just going to put the module behind the drive, put it back into the host system again. Now, obviously, the drive module offsets the drive slightly, so it won't actually click in place. However, it will be sitting within the cooling envelope of the server. We then plug it in this case, to our larger rack mount controller, and then you're ready to go. It's very, very simple.
The modules are intended to fit within the same footprint as the drives. So we should be able to plug this module into, and we can plug this module into pretty much any system that's out there. The only time we'd ever see any issues is where the offset of the drive causes a conflict, which might be in a vertical system. But even then, we have solutions to solve that problem. So these are very, very versatile products. You might buy them for one project, and then you might, or you would apply them to many other projects as time goes on.
So as well as just the drive modules, we have, as I said before, the entire range to instrument every removable part of the system. So for many people, it will simply be the drive and host interface they're interested in. However, perhaps if you're developing a full storage enclosure, well, we can instrument SAS, SATA, and NVMe drives on the front of the system, and then on the back we can instrument all the cables. So that might be mini SAS HD, external PCIe, it could be RJ45 or SFP high-speed Ethernet. And all the modules can be controlled with a very similar command set in a similar way with the same controllers. So all of our modules are compatible with all of our controllers. So if you move from SAS to NVMe or from Gen 3 to Gen 4 to Gen 5, the same controllers and the same test suites can be used, and all you have to do is replace the module. So there's a couple of examples of scaled up testing here. Now, many of our customers gain huge benefit just by having a couple of Quarch modules on their bench with their drive and host setup to do basic hot plug and fault injection testing. In some cases, however, our customers have found major benefit in scaling up into larger systems. So we've got a couple of examples here. The first was in a drive qualification system at one of our large US clients. So they found that the batches of drives they were receiving from different suppliers were not always consistent in terms of the reliability. So what they began doing is racking up 24 drives in an enclosure and basically hot plug cycling them to death. So 10 seconds up, 10 seconds down over a period of a week, and then analyzing the number of failures and how early those occurred. And with that, they could then qualify things like the hot swap circuitry on the drives and how reliable they were to enumerate.
So this customer was receiving drives from many different vendors. And the first thing they would do is take 50 of those brand new drives of any model, put them into a rack and power cycle them relentlessly for a week and find out which ones just survived that week. So it was a pretty brutal test, which before Quarch was carried out with interns mostly. That they found that very useful for establishing whether there was some hardware problem with the drive.
And of course, when knowledge of this came out, it began to change how the industry viewed the testing of hot plug. Because of course, if your major potential clients are doing this form of testing, realistically, you then have to test it yourself if you're designing drives to make certain that you're going to pass these qualification tests. Now, the second system on the right was actually a RAID system. So although the setup's quite similar, it was a completely different set of tests they were doing. In this case, it was a large storage company again. They had a multi-enclosure RAID system and previously a system of manual tests, which took 2 engineers roughly a week to complete, pulling out and inserting drives in a very specific sequence to test RAID rebuilds and fault detection. What they were able to do was automate this with the Quarch system, leading to the test running over around 48 hours with no manual intervention whatsoever. It also meant that every time that they had a new version of the firmware, new RAID updates, or a new set of drives to test, they could simply set up the system, leave it running overnight, and run those tests again and again, getting far more data far more quickly as to whether they're making their software better or whether they've introduced potential problems.
So this system on the right-hand picture has 3 different types of RAID array in it. So it has 3.5-inch drives in the top, 14 or so. It has, I believe, 24 2.5-inch drives in the middle system, and then the one at the bottom with all those white extensions is a 48 3.5-inch drives in a vertical configuration. So that's one of these slightly odd configurations. But every single one of these drives is instrumented with the same module. It doesn't matter that the form factors are different. And there is a script running which is able to disconnect any one of those 50 or so drives, 70 or so drives we just talked about. So any of those drives you can see, we can fault them, we can pull them out of the system, and we can cause a failover from primary to secondary port. So it's a very powerful system. So
the form factor of the other modules is slightly different, although their actual functionality is very, very similar. So when we instrument cables, we tend to have an in and out philosophy. So on the top left there, we've got a 12 gig mini SAS HD. External PCIe is a very similar form factor. On the bottom left, we've got RJ45. On the bottom right, we've got a quad ganged QSFP. So while the form factors can be different, and some of these are rack mountable as well to improve the cabling, the actual functionality is virtually identical to that we'd see on the drive modules. PCIe form factors come in a wide variety as well. So as well as the U.2 SFF for the drives, we've got a by 16 AIC module here on the left and a M.2 on the right in vertical configuration, so that it can fit within most standard servers. Whilst PCIe slots don't support hot swap necessarily, the modules are still very useful and are used across the vast majority of the drive designers in the US and worldwide, who use them for basic removal and insertion of the drives at various times during their tests, and also for a huge variety of fault injection, for automatic lane reduction, for instance, and a wide variety of other tests.
I think surprise power loss is one of the biggest use cases for these. It's very, very easy to do that with these modules. They're also used in many cases to bring a drive back once it's got into a fault condition without having to power cycle the whole system, although that does require some knowledge of your own drivers to do that. Another thing that we see that people are very interested in terms of these is in simulating different power up and power down timing scenarios. So by that, I mean that in PCI Express, there's a very clear relationship between power, burst, ref clock, and data in terms of the time that those different signals will become active from the motherboard. So if I have a new PCI Express product, I might do 1,000 hours of testing on a single motherboard or model of motherboard. And that motherboard will almost always have the same power to burst, to ref clock, to data timing relationship in terms of power up and power down. I then send that to my customer. They have a different manufacturer of motherboard, which has a different relationship in terms of the timing, and my product fails. And so what we can do with these modules is we can set, to some extent, the timing between these different signals on power up and power down, and we have a lot more test coverage than would otherwise be possible with one particular motherboard.
And we had, so a year ago, we had a major drive vendor with exactly this problem. They were sending the drive into the customer and were told that it doesn't work in our system. Now, the customer was able to take a scope trace of the timing differences. However, the drive manufacturer had no way to replicate them. So they came to us. They were just preparing to fly a team of 3 engineers across the country to try and work out what was happening. However, within a couple of hours, we were able to give them a script to run on the slot breaker card that just simulated that same timing, so they could repeat the problem in their lab, allowing the R&D engineers to come up with a fix much more quickly, much more easily, and get it straight out to the customer.
We had another customer who was making a RAID card, RAID adapter, and they would find that on certain power loss scenarios, they would corrupt their data. And this was a very similar situation. They found that the ref clock was going invalid faster than they'd expected, and that was causing their RAM to be corrupted. So we've seen a fair few significant real-life bugs based around these timing relationships, and many around just straight power loss as well. So pulling power, surprise power loss testing on drives and adapters is a real favorite amongst our customers, and these modules make it very, very easy to do that.
And of course, a lot of this is also assuming that everyone is meeting the spec. And then you're testing to the full range of the spec. We've also had information from the industry, from some of the experts who've indicated that not everyone is even precisely following the specification. Sometimes the timing that your device may be exposed to will actually be outside of the spec because someone else has done something wrong. Now, whilst that's not necessarily your fault, it's certainly going to be important that your drive does not lose data or severely fail. It's going to have to handle the unusual scenarios correctly. And again, that's something that we can create here. So the control options, again, this is a modular system. It's designed to be very simple to start out with and try out. So at the top, we've got our single port interface kit. It's cheap and effective. You can plug it into your laptop or your PC in the lab, connect one module to it, and you can control either via serial or USB. You can do that either from our TestMonkey application, which allows you to do basic manual testing very simply, or you can script via the Python API. in a few minutes. If you need to control multiple modules in a system, then we have 4 and 28-port rack-mountable controllers. Of course, they can sit in a bench as well. The 4-port controls can be rack-mounted side by side in one U, so you can have 4 or 8 ports. Controllers can also be chained together to create larger systems if necessary. And of course, if you finish up testing on one product and you want to move to something else, all the controls can be reused with other modules. The scripts behind it will be virtually identical, and you can change the controller configuration as needed. Controllers can be run from serial USB and LAN, so you can control them across the network. All of our control options are very simple. They use industry standard systems like UART serial, Telnet, HTTP REST control. The interfaces are open and clearly described in our manuals, and our Python API makes it very simple to operate them in practice. For instance, if you want a Python API, a single Python command will download it from pip and make it accessible on your system, including everything you need and all the drivers in a single command. We have a range of application notes that can be downloaded from our website that give you examples of controlling the modules and of standard useful tests. We also will be introducing the Quarch compliance suite. There's a beta version available on our website now, and it's going to be extended month by month over the coming year with new tests. And the idea here is that if you don't have the skills or experience or time, of course, to actually write the automation scripts to do the testing, then we'll be providing a set of ready-to-go tests with basically one-click test start, anything from 25 to several hundred or even 1,000 test points of different timing scenarios can be run through automatically, and you get a report at the end of exactly what passed and failed.
Yeah, Quarch Compliance Suite is intended to build upon the work we've done with University of New Hampshire and the NVMe integrators list. So, as Andy mentioned earlier, if you're going to be qualified for the NVMe integrators list, then you need to go through a Quarch hot plug test. But it's a relatively simple test. And now what we're doing is we're building a far more complex scripts. So you can buy Quarch Compliance Suite, you can do a one-click script, and it will do many of the things we've talked about. So it will cycle through many different power up and power down timing scenarios. It'll create faults, and it will check the status of the drive before and after each of those events. So you'll end up with a comprehensive report on that drive. So this might be used if you go between hardware. It might be used if you go between firmware revisions, because it's very simple. The idea behind Quarch from the start has been that if we make comprehensive testing very quick and simple, then you can do it much more often. So every time you do a new firmware version, you'd run through the same script and you check. If you get a new drive if you're buying drives, and you get a new drive firmware or a new drive model from your supplier, then you'd run it through the system and check that everything looks the same. So it reduces the risk considerably and makes life very easy. And it builds on the experience we've gained from different customers. So we have all these interesting stories of where products have had issues in the past, as we mentioned. We can't share those exact cases, but what we can do is put those cases into our scripts so that they're beneficial for many people.
And it's not just repeating; it's also how early can you test. The earlier in a design process that you can test and get results back, it dramatically reduces the costs. Now, I've been out in Israel recently, and there's where we had a whole cascade of problems between a silicon company, a drive manufacturer, and the host company that was actually using the drives. And at this point, the drives had just started to hit market. The systems were going out to customers, and then they began finding problems. And at this point, everyone in the company, from the engineer to the CEO, are all pulled into panic meetings. Everyone's desperately trying to find out what's going wrong. They're buying test equipment everywhere to try and track it down. And this is completely the wrong way to do things. It turned out to be, again, hot plug related problems between the silicon on the controllers and the drives. And if that had been tested a few months earlier during the design phase, it would have cost them 80% less, both in terms of time and effort. If it had been done during the initial design phases, research and design phases further back, it might have been found almost instantly and fixed long before it had any cost effect at all. So the earlier you can do this kind of testing, it can produce huge benefits for the company. So the next thing we're going to look at is the power range. So as we said, these modules are great if you just want to cut signals and interrupt things, but what if we want to do power loss in more detail than just turning the power off. So the Quarch power module was created, again, working with one of the US major drive companies who were looking for a better way to test their products. So what we've done is, in this small compact unit, is that we've built in a dual channel programmable power supply, so we can do full range power margining for drives. We can also measure power accurately and for a long period of time. So these products can support both SAS and NVMe drives with a dual rail, both 12V and either 3.3 or 5 volts. We can control them via USB or LAN. Again, we've got simple automation and powerful software suites to go with them. And in the larger rack system, we can have up to 6 drives simultaneously in a 19-inch rack form factor. The difference here between most other forms of power testing is there is no need for current probes, custom cabling, or similar. We have a set of simple plug-and-play fixtures that look very similar to our breaker modules, but in this case, we're routing the data directly through, so we're not disturbing it at all, and we are supplying power from the outside. That means the Quarch power test system can be set up in literally 60 seconds. Just click one of the interposers in, put your drive on top, plug it into the power module and turn it on, and you're immediately ready to go. So we can deal with by16 slot devices, M.2, U.2, U.3. We can go into custom cabling looms with our 4-pin Molex adapter, for instance. And this makes it easy for even a student or someone who's not particularly familiar with power testing can set this up almost immediately.
Instrumentation is really, it makes a huge difference here. So if I want to test my PCIe slot card previously, what do I have to do? I have to find a place to cut, put a wire in there, put a current probe onto that wire. Now, current probe comes with a scope. Typically, it's not something you want to have on your desk in your cube. Some people do, but those are the more specialist guys. With this system, all I have to do is pull my card out, plug the fixture in, plug the card on top, and I'm ready to go. And I haven't modified anything at all, so I haven't damaged any equipment, and it's just far more effective.
And of course, the next problem is if you're simply using a scope, then you don't have any ability to drive power and actually do power margining. You can only do the measurement side, whereas we can do the both here. And then another problem is that a PCIe slot device is normally expected to power up at a very precise time that the motherboard expects. If you are providing your power externally, you have to find a way to synchronize that, which can be rather hard. With our interposers, the synchronization is built in. So we will supply power from our device at exactly the same time as it would have been supplied by the host. The drive will come up as normal and you're ready to test immediately. So as I said, it's a fully programmable power supply. So with the linear regulators, we can regulate from 0 volts to rail nominal plus 20% for overmargining. We can do so with the pattern resolution of 1 microsecond and a fast slew rate at roughly 1 volt per microsecond. So we can create very complex, very fast moving patterns to simulate almost any power scenario. Now on the left-hand screen there, we're glitching. We're pulling the rails down, but not all the way to ground. We're pulling them down to a set voltage. Each rail is going down for a different period of time and at a different time.
Yeah, so on that, it's a small picture, but on that left-hand grab there, what we've got 2 points in each pattern. Now, a pattern can have up to 1,000 points in it. So these are very simple patterns to do to these. And simply we have it at time 1 millisecond, I want to drop by 6 volts, which is 50% on the 12 volt rail. And then at time 2 microseconds, I want to go back to nominal. So that's a pattern. And of course, that voltage can be anything you like, and the times can be anything you like. So we can create interruptions, anything from a microsecond, subject to the slew rates, up to permanently or many seconds.
So on the right-hand side, for example, we've used a few additional pattern points, and we've created a particular scenario where both rails are ramping up at different rates. However, the 12-volt rail has a couple of notches taken out, it simulating other high-power devices coming onto the rail and temporarily pulling the rail down. So that's a nasty scenario for a drive to deal with, because it may have just started to initialize and turn on, and then suddenly it briefly loses power. What's it going to do? And there is a vast range of potential brownout, glitch, power loss tests that you can create with this.
Yeah, and they're very, very simple to set up. So if I want to ramp my power, it's a single point in the pattern. It's simply 10 milliseconds plus 12,000 millivolts, or 20 seconds plus 11,000 millivolts. It's very simple to set up these different ramps and interruptions.
Now, one of the very standard problems that we've seen in customers, probably affecting almost half the drives we've tested, is a failure of their sudden power loss circuitry. So the simple test is that we pull both rails down hard to ground for 1 millisecond. And what we're testing is that the drive detects the sudden power loss, the hard short, and isolates itself from the rail so it can use its internal capacitance to shut itself down nicely and save the data off the flash. What we found on multiple drives is that they don't isolate themselves fast enough. We actually discharge the capacitors. There isn't enough power to shut down cleanly. And there's either data loss or in some cases, the drive is permanently failed.
That's right. So the test we would tend to run is a millisecond interruption on 12 volts. So that's the one the demo we used to use. In reality, we're 1 volt per microsecond. So that would take about 12 microseconds to go from 12 volts down to ground. And what that's simulating is a power supply crowbar, so that the power supply is not just drifting off, it's actually being pulled hard to ground. And that's a scenario that's very difficult to simulate in any other way other than applying a screwdriver across your capacitors or something equally brutal. And as Andy says, what happens is the drive simply can't isolate itself in time, and then you'll see data corruption or even some physical damage to some drives. Now, that's a very, very aggressive test. But of course, we're fully programmable, so we can do that power down over a millisecond, over half a millisecond, and keep working our way down and see where the limits are in that. So it's a very effective tool.
And of course, while it's an aggressive test, power supply crowbars are things that happen in reality, and people do drop screwdrivers into machines. Yeah. So it's very important that, for instance, someone dropping a screw in a machine does not cause every drive in the rack to suddenly lose all its data.
Of course.
It would be disastrous. And it is such a simple test to do. So the next we developed and released over the last couple of years is called Power Studio. Now, the idea with this is it's a fairly comprehensive analysis tool for looking at the power recording. So if you have a scope and current probes, you'll be able to capture an area of power data. Maybe it might be a few seconds, it might be a few milliseconds, depending on the resolution you're looking at. With Power Studio, you can record almost indefinitely and at high resolution, or certainly at a high enough resolution for almost any form of testing you'll need. So what we've got here on the bottom of the screen is the timeline trace, and we can see a bunch of little spikes that's occurring over a period of a few minutes. Zooming into 3 of those, you can see that the spikes are actually full power cycles of a spinning drive. And we can zoom right in again into 1 power cycle, and you can see the level of detail that we've got as the sudden spike as the bladder starts to spin up. And then towards the right-hand side of the image, the small little jumps as the head is seeking back and forwards on the disk. So we can zoom right in to look at the detail of what a drive is doing, everything from inrush current on the capacitance as they charge, or zooming right out to look at the long-term trends of power consumption over different workloads.
So between the HD power modeling modules and the QPS, Quarch Power Studio software, we can stream at 125 kilosamples a second. So we're looking every 8 microseconds at the power on all the rails. And we can do that indefinitely. So what's happening is we've got a network connection or a USB connection, and that data is being read off the power module. And as long as we keep reading it, the power module will keep providing it. And so we have customers who've done 1,000 hours of testing. And what they'll do is they will start recording, and they will run many different workloads to the drive over 1,000 hours. In their case, what they're looking for is that the power never goes over the required threshold. So 15 watts for an M.2 or 25 watts for a U.2. And that's simply it. And some of the other features we have, which we will be coming to, is that we can automatically capture that data. So we can annotate the test file, and we can show where our test started and stopped. So in the image we've got on the screen now, we're seeing that what we've got is a Python script. And the Python script has gone out, it's found a drive, it started sending different workloads to that drive, and every time it does it, it is telling QPS to analyze the trace. And so we've got these red annotations on the trace, which can be whatever you want them to be. So in this case, we are annotating the iometer workloads. But if you have some of your own data, so if you've got some log data that could be in there, some other metric, then you can put that in as an annotation.
So we can also add custom channels. So as with a standard scope, we can display the voltage, the current, and the calculated power. Also on this, however, we are adding the IOPS. So we're running traffic from, it could be from FIO, it could be from Iometer, it could be from your own internal traffic generation tool. We're annotating the start and the end of each test, and we're also adding as a custom channel the performance. So now we have power versus performance on the same graph. Perhaps you would have something like drive temperature to monitor as well. That can also be added to the trace.
So in terms of the automation, the Python script that's behind this is simply saying either annotate my file right now, in which case it will happen in real time, or you can back annotate the file. So in this case, Iometer gives out a file of performance every second or so. So in this case that you're seeing here, what the script is doing is it's running, say, 10 seconds of workload. It's then looking at that Iometer file with results for IOPS and performance, and it's back annotating into our trace file. So there's a lot of flexibility there to do what you want. So it could be anything. It could be Q depth, it could be IOPS, it could be temperature, it could be all sorts of different metrics. It's up to you to decide what you want to put into that file.
And now, of course, I mean, this is only 4 different workloads, but we could have 1,000 different workloads run overnight. So the question then is, how do we actually analyze that data? And what we can do is we can automatically calculate statistics across those annotated regions. So if you've annotated the start and the end of each region, then we can see here we've got 4, 16, 32, 64, and so on, automatically annotated for the block size. So then with a single click, you could order by average power, by maximum performance, and you can immediately start to see which of your workloads have the best and worst cases, whether it be for maximum power. Mike says you might be going over your threshold, which workload does that, or it might be a question of what's the best balance between power versus performance. And because you can gather a huge amount of data this way, you can then start to tune your software and your firmware to get the best possible performance out of your devices. Again, the automation options for power is very simple. It uses the same Python APIs we use for our breaker module. So if you're familiar with one, then using the other is very easy. Again, we have a set of application notes, as with the breakers, giving you examples of how to use the power modules, how to do margin glitching, how to do complex measurement and saving data. And that data can either be in Power Studio, as we've seen, or it can be exported into a simple CSV format for your own post-processing. Behind the scenes, we have Quiz, the Quarch instrument server, which is a simple Java application which allows direct access to the raw data. So that gives you easy automation. It can be run on a system that doesn't have a graphical environment, fully automated. Or you can go via Power Studio, which gives you the analysis and pretty viewing of the data traces, so you can see what's happening in real time and then annotate and share that data with other people in a useful way.
So Quiz, Quarch Instrument Server, is a console application that does the handshaking and buffering of data from the Power module. So Quiz can be accessed from a script, or it is used by QPS in this case. And the reason we have to use Java is it's the performance over Python. So it allows us to reach those high streaming rates. We then have QPS, which is the Java GUI which sits on top of that. And we've run it successfully on Mac, on various flavors of Linux, and on Windows. So we're trying to be truly multi-platform with these tools as well, which is important. It's also worth noting that these tools can all run on any machine. They don't have to run on the host. And for a lot of our customers, performance is incredibly important. So they don't want to burden the host with extra cycles. So we can run Quiz and QPS on different machines. They don't have to run on the, yeah.
In terms of support, all these products are available from Saniffer as our regional partner. We can do evaluation units. Obviously, Saniffer can help with repairs and imports and quoting as well. Regardless of that, you have direct support from the Quarch engineers. So the likes of myself and Mike will still be aware of every support case that comes into the building. And support cases will be directly answered by the engineers who designed the products, meaning that you get the right answers very quickly. If you need help in getting an evaluation system going, we can take a direct call with you, or we can help you via email. We also have a strong warranty service on top of the standard 1-year return to base warranty. We also offer easy and low cost repairs, even of our much older products. Even in the case of a product that's 5 or 10 years old, we've generally been able to repair it at a low cost and get it back to people.
Yeah. We've been in business 13 years, and we've never refused to repair a product. We believe in fixing our products. So we have 12-year-old products out there which are coming back to us and being repaired and put back into use.
And still, of course, being useful for the companies that have them.
We're very proud of our support, and we try hard to make sure we look after our customers.
So what we're going to move on to now is a quick live demo looking at the breakers in TestMonkey, just so you can see a little bit of how it actually works in practice. And then we're going to have questions and answers at the end. Jordan will be helping us with that. So I've got one of our modules on the bench, just attached to my laptop. We're using a Gen4 U.2 breaker module at the moment. So this is TestMonkey. This is our graphical tool for controlling modules. It's not normally used in the long term. Normally you would use a Python automation to get the best out of the modules. However, it's great for evaluation, for training, a bit of manual testing, and just trying things out to understand how it works.
And for debug as well.
So I'm going to connect to the module, so we have control now. By default, the module's plugged, so the drive is powered up, everything's running as normal. I could have data going as necessary. If I click pull, I will immediately pull the module. So that's equivalent of me walking up to the rack, possibly walking into another lab even, and physically pulling the drive out. I can then plug it back in again. So a simple click will immediately trigger that action. And the next question, well, what precise action did I trigger? So if we look on the hotspot patterns, as I mentioned before, we use default timings, which are carefully calibrated to work exactly as a drive would do if it was pushed smoothly into a system. And there's actually a white paper available on our website, which covers a lot of our research into this and testing in terms of what hot plug speeds actually happen and how pin bounce works in practice, which makes for interesting reading.
Yeah, the 25 millisecond timing is a good average figure. The reality is that the time for a hot plug, certainly on a drive that's in a sled, will be very dependent on the system it's in. And so the latching of the sled will dictate how quickly the hot plug occurs and how clean it is as well. So there's a mechanical element.
And of course, how aggressive the user is in terms of pushing. So what we can see here, we've got 3 different sources set at 0, 25, and 50 milliseconds. These are timing sources within the module that we can control very simply. For instance, if we wanted to move to a faster hot plug, I can change this one to 10 milliseconds. And then instantly we have a more aggressive step at the first part. I can also simply click and drag these as well. So almost immediately there, if I was to do a plug and pull now, we would get this faster hot plug scenario. Next, we have the signal assignments. So we can see the range of groups here of the standard sets. And if I look inside the all group, we can see that these are every single signal on a Gen4 U.2 module that's controlled.
If we were to look at those closely, we can see that we have a single signal on source 1. Now, if we go back to our patterns, we'll see that source 1 happens first, followed by source 2, followed by source 3. So source 1 equates to the longest pins, the pins that will mate first in the connector. Source 2 equates to the medium length pins, and source 3 equates to the shorter ones. Typically in a U.2 connector, there are 3 different connection times because you have 2 lengths in the plug and 2 lengths of pin in the receptacle. Which gives us these 3 options. And interface detect happens to be on a long pin. Because of backwards compatibility, the pin lengths were chosen in an original SAS drive. So this used to be a ground pin, which is why it's very long. And it's now become source 1, now become a long pin. And then we have a few on source 2. So these are, so power disables the source 2 pin as well. So that's a medium length. And then pretty much everything else is a source 3.
With the exception of 12-volt charge, so the charge pin obviously meets first.
That's right. So in terms of the charge, what you've got, the intention is that the charge pin has a current limiting resistor behind it. So the charge pin will meet. Inrush current to the drive will be limited through that resistor and will start to charge up drive capacitance. And sometimes later, the power pins will then be connected. And there is no resistor in place. So the second those power pins get connected, if your drive capacitance is not charged adequately, it will be a very large inrush current, and we might see the host system drop out of regulation. So if I was interested in causing a difficult hot plug, one that might stress the host system, I would reduce the time between source 2 and source 3. So I'd effectively make my medium pins and my long pins mate at the same time. And that would mean there was no time for the drive to pre-charge. So it would be very difficult. There would be a lot of inrush current would occur.
And of course, we can select any of these signals onto any of the time sources to create a whole range of complex scenarios. We can also control them manually at the time. So for instance, if we select source 0, it's always off. The signal will always be disconnected regardless of the state. So at the moment, everything's plugged in. I can say, well, what happens if I disconnect 12-volt charge? So this simulates a broken pin or a failure in the track. So 12-volt charge is no longer connected. However, the power is still connected, so the drive is probably going to work fine. However, if we were to do a power down and power up, now we'd be doing a power up with no 12-volt charge. That means there would be no pre-charge. That means there would be a significantly faster inrush current on the power pin. And again, as Mike said, that could cause the supply to go out of regulation or something unusual to happen. We could invert that test. I can reconnect the 12-volt charge, and I can disconnect the 12-volt power. Now, depending on how the drive is designed, it may immediately realize the power has gone down and shut itself down. Or if the drive is idle, there may be sufficient current on the charge pin for the drive to continue working, and it will appear to be correct in the system until you try to run traffic to the drive and it requires more power, at which point you'll get a very unusual brownout scenario. And we don't know what's going to happen, but it might, in the worst case, result in corruption or loss of data. And again, this is a type of test that, although it would be theoretically possible to create by other means, it would be exceedingly hard, whereas I've created that scenario in a couple of clicks in a matter of seconds.
Yeah. It's also, it's worth saying that in TestMonkey, we have a thing called script viewer. And so everything that we do in this user interface has an automation command associated with it. And so what I can do is I can build up tests graphically in this interface, and I can look into the script viewer and I can see, so Andy originally, he pulled the power on the drive, he hit the button that said pull power down, so that the command that we'd send to our module is simply run power down. Run power up, plugs it back in again. And then Andy started changing delays, and you can see the commands are all in here. And so anything that you do in this GUI, you can actually generate a script very quickly from that, because you can take this and you can cut and paste it into whatever other scripting interface you're using, and you have the commands right there.
So in many cases, you won't even have to go as far as reading the technical manual.
So we have these signal groups. So in this all group, we have every physical signal that's on the connector, with the exception of the ground pins. I can see them all in here. So what if I want to turn off ref clock, or I want to turn off a particular port? It's not very convenient to come in here and do the signals individually. So we have signal groups for that. So these same signals are collected into groups. And so lane 0, we have the transmit pair and the receive pair. And I can turn off any of those signals individually if I want to, or I can turn them off as a group. So if I wanted to fail lane 0, I simply go to my lane 0 group and I assign everything to source 0. And that's turned that whole lane off. So we talked earlier about a redundant port failover. So this is a dual ported module, so it has a port A group and a port B group. So in port A, I have all the signals which are associated with port A, and similarly in port B. So if I want to fail the primary port in this drive, I just go to my port A group and I turn that group off by applying it to source 0. And I've just killed my primary port, and now the system should be failing over and running on the secondary port. So very, very simple to do these fault scenarios. Similarly, we have the clocks and the sidebands. We have many groups in there for useful signal families.
And just the few tests that we've done here. Now, obviously, we're not actually verifying that the drive comes back each time and that everything's correct. However, the level of fault injection that we've done in maybe 2 minutes of testing, if we'd actually tried to do that on a real drive in a real system, you're probably talking about 4 to 5 days of work there for an engineer to create that set of tests, and it would probably have involved the destruction of various drives and connectors to do that. It's simply not practical. Whereas in this case, we've made a set of fairly critical tests, fully practical to create and to repeat. Now, glitching, for instance, is very similar. So we've seen a lot of cases around ref clock and similar timing where we have problems. So for instance, I could simply select the clock. I can enable it for glitching, which means that we will be enabling glitching for both sides of the differential pair for the A ref clock. On the Actions tab, I can then select the glitch length. Now, if I was to say glitch once, I would immediately generate a 50 nanosecond glitch on that ref clock. If I wanted a PRBS ratio, I can set the ratio and start it. And then I would be creating a 50 nanosecond ref clock at a ratio of 1 in 4,000, which means if we were to split time up into 50 nanosecond blocks, 1 in every 4,096 of them on average would be glitched. However, it would be done in a bursty randomized fashion, creating a bad link. And that is, being on the ref clock is likely to cause a whole range of problems. We've seen cases where, especially during the plug and pull event, where just a few additional cycles or a few fewer cycles of ref clock is the difference between a perfect hot plug event and a total failure and corrupted data. So the ability to create these simple interruptions make it very easy to verify that.
It's also it's challenging as we move, and there are now the SRIS and SRNS systems. How do you test those on a system that has a ref clock in place? And so this module gives you a very simple way of turning off the ref clock and making sure that you can actually do that.
We recently took part in the test setup calls for U.3 at the University of New Hampshire, and these questions came up again and again. So the drive is supposed to support SRIS and SRNS, but how do we prove that just because we've told it to move into a certain mode that it is? There were lots of conversations around cutting cables or having special test fixtures made. However, in the end, of course, the Quarch module was chosen as by far the simplest way to make sure that your drive does not need ref clock, is to make sure you have turned off ref clock. You then have absolute certainty that you're supporting the correct mode. So we have a number of videos on our website to just give you a good idea of how these products actually work. Let me just, so this is an equivalent power setup that we put together in our lab is in comparison to the power module. So what we've got here are two different programmable power supplies, because that's what we had available. We've got a scope on top, we've got dual current probes, and we've got a bunch of custom cabling connecting it up to a drive. It's unwieldy, it's complex, and it took a significant amount of time to physically find all the parts and put them together. In comparison, however, we've got the Quarch module set up, and you can see setting it up here. Put the interposer on the back, plug it into the system we're using, plug into the system, start up Power Studio, and we're measuring power. It's literally 60 seconds to set up and gain the similar level of analysis. Because we don't actually possess probably the equipment in the lab, even though we have a lot of expensive test equipment. I'm not even sure we have the parts available to do a similar level of testing without this module. This is a similar setup here using an AIC slot module. So in this case, we've got one of the latest Intel Optane drives plugged into our injection fixture. So this is the kind of test that the drive manufacturers, the likes of Intel, would be doing in their labs. And these Quarch modules for power testing, we've been pushing a lot into the major US designers. So several of the major US drive design labs are moving towards the Quarch power module as their standard system for power testing. And that's because both of the cost, the flexibility, and the level of automation and power capture that they can get. Here's another example with EDSFF, with M.2, with U.2. So the full range is there. You see we can export all the data straight out to CSV. Sorry, we can jump and zoom in, and this is while we're recording. We're jumping back and looking through past data and at high resolution. This is far, far more convenient than using a scope. The statistics are calculated in real time, so whilst you're recording, whilst you're jumping back and forwards and moving your annotations. In this previous example here, if I just jump back, we're doing this is actually running part of the Quarch Compliance Suite demos. So what we're doing in this case is that we run Quarch Compliance Suite, and we're doing power margining on the drive, and we can see the blue line for power has dropped down between one test case and the next, so we've margined the voltage down. We've annotated the start and the end of the test, and we also have marked on here that the drive re-enumerated. So we can see how long it took to re-enumerate at the different voltage levels. We can see the difference between capacitance inrush and total power consumption at each voltage level. And all of that is displayed neatly in this analysis, which of course can then be saved off and shared with other people or stored for use later.
Yeah, the power of automation here is great. So we have two ways of doing this. So Quarch Power Studio can be scripted through Python. So you can create your own script. That script might do margining, so it might go -5, 10%, +5, 10%, do different ramps, different interruptions, and kick off different workloads. And every time it did that, it would annotate the file to say what that test was. The other way to do that is to use Quarch Compliance Suite. Now, we talked about Quarch Compliance Suite earlier, and we talked about it in terms of the breakers mostly, but Quarch Compliance Suite can also do power. We'll soon be releasing some scripts which are, again, one-click scripts. So you buy Quarch Compliance Suite and the equipment, and you say, go, plug a drive in, and it will do performance versus power. So it'll run a bunch of different workloads you can specify, and it will tabulate and record the data for it, and you'll be able to look through the data. So it's a very, very powerful system.
Right. So does anyone have any questions they'd like to raise at the moment?
Yeah, you mentioned about the Quarch Compliance Suite, the version 1.01, and that is a very early version, right? So is it free for customers?
So the Quarch Compliance Suite is now in version 1.03. It's available on our website.
Okay.
So at the moment, there are 2 test suites that are available for customers to run for free, with the additional test suites being added are licensed. So what you can run immediately, and by far the most useful one, is the UNH IOL hot plug test suite. So that replicates exactly what any drive vendor would have to do if they go to one of the UNH Plugfest events. Now, I know last year UNH actually ran an event in China, and in many cases, when I've done the US events, I've seen Chinese companies come across and test their drives there. We have 2 options. You can either run these tests by downloading and running our application note, which implements these tests in Python, or you can take the Quarch Compliance Suite, which gives you a nicer graphical control over it and clearer results.
So Quarch Compliance Suite licenses per protocol, I think, or per test script anyway. And right at the moment, it's really quite cheap, or we'd say it's very cheap. It's in the region of a couple $100 for an annual subscription, I think. It's kind of a soft start for Quarch Compliance Suite. So you can download it right now, you can run it, you can run the basic scripts, and you can decide what you think. And then
we're continuously adding new scripts over the coming weeks and months, which will expand it rapidly. But for now, regardless, I recommend that anyone that's designing or working and getting compliance for a new SSD should be using those UNH IOL tests long before you look at going to a Plugfest, and just making sure that your drive supports them. Similarly, we have that voltage margining test in there, which can be run automatically if you have a power module or if you just have an evaluation module.
Okay. So one engineer asked the cable support high and low temperature, like I think probably he asked the low temperature -40 and high temperature 85 Celsius.
For the cables, the drive modules themselves are environmentally rated within the manuals at a fairly standard lab range. I think between 5 to 40 degrees probably. Now that's what we test to for safety purposes. In practice, we've had a number of customers run well outside that range. The modules are relatively simple. So the processors, for instance, I believe are spec'd up to 85 degrees. I mean, obviously, if you're doing substantial temperature cycling, especially if there's any humidity risk in there, there is potential for damage. But if you're simply running at a high or low temperature, the modules will probably operate fine across the majority of those ranges.
Over the years, we have had a number of customers run these modules in environmental chambers. Now, the humidity is much more of a problem than the temperature to some extent, although extreme temperature cycling obviously will degrade the module. To my knowledge, we haven't had a failure due to temperature.
I believe in the vast majority of cases, the temperature damage will be more of a problem for the drive that you're testing than it will be for our modules.
If our customers are being sensible with the product, not dropping them and crushing them, we're very happy to support that. And so the spec for a cable is 5 to 40 degrees centigrade, but we have customers using them in thermal chambers, and we will repair them subject to our normal problems. So we're very happy to work with that. We're happy for our customers to try it out with evaluations as well, as long as they tell us first and make sure it's suitable for their purposes.
Yeah, okay. I think that Mark asked this question because he wanted to put that breaker, the swap modules, into environmental chamber. Low temperature, high temperature, humidity is like 95%, something like that, I think. Yeah.
So Mike was just saying that humidity is the obvious problem, especially if it's condensing humidity. Unlike a drive that is potentially sealed, at least to an extent, these are open modules, so you have to consider the test you're applying to
we would be happy to support you take an evaluation module and put it in there and run it through cycles and check that it fits your needs. That would be, we'd be very happy to support that. Yeah. And then if it looks like it's good, then we would continue to support that going on.
Okay, I just explained it to you, Mark. So he understood because they wanted to put the hot plug modules into an environmental chamber, you know, the low temperature,
yes.
high temperature, and humidity. Yeah.
Mm-hmm.
So, but last year I visited one expo in Shanghai, and there is one company in Hong Kong that you know they have a very special liquid. If you put your PCB board into that liquid and you get it out, right? So so for that PCB board, there will be no problem to put it into the water. It's still working in the water, no problem.
We'd be very happy to find ways to make it work. We have had people use them. I think we'd be happy to supply an evaluation board that they could put in their chamber and cycle and see what the results are.
Yeah, and if we need to look at some form of coating for the humidity, then it's something we could look at, certainly.
Yeah, because some customers asked me before that they wanted to put the hot modules into the chamber. Okay, but we didn't talk into the details because on the data sheet they put something like you said 5 to 40.
I believe it's 5 to 40 degrees, but that
right?
is
that is operation temperature, right?
Yeah, that's both us being careful, and it's also it's the range that we have safety tested at, so that we know it's appropriate.
Okay.
Outside of that, then obviously, you know, a customer doing something else needs to take their own risk assessment and discuss it and be happy with what they're doing.
But we're happy to work with the range. The temperature range in the manual is the safe temperature range that, you know, everyone can use it at. But we are happy to work with customers who want to try and put these in chambers. So we're happy to support, you know, putting one in there for a number of cycles and seeing what the result is, and also looking at coatings and different things we could apply, and just coming up with a sensible solution. It doesn't mean that we're replacing cables every week and make sure that it works for them.
Okay, understood. So next time, if the customer they do not care about humidity, if they only do low temperature, high temperature, maybe we can get them evaluation kit for trial and see, right?
Yes.
Yeah, I don't think there would be any problem with temperature. I think temperature would be fine. For humidity, we might need to look at coatings, but I would be willing to let them try the humidity as well.
Okay.
Again, the big difference there depends whether it's condensing humidity or not. Yeah.
Okay. With two questions. The first one is about the hot swap modules for PCIe Gen4. But I just lost his voice.
Okay, we can wait. It's fine.
Yeah.
So the data control switch between the host and the device under test.
Yeah, the
signal compensation.
Yeah. No, the compensation, I assume signal conditioning is how we would say that. For PCIe Gen4, no, we still have an entirely passive architecture. So we use a passive RF switch, and that is all. So we have loss of it's around about 3 to 4 dBs going through our module, compared to the margin in the PCIe spec is closer to 30-40 dBs of loss. So we do not need to do any signal conditioning because we're well inside the margin that's allowed in terms of link budgets.
And in practice, of course, these modules have been used in virtually every major designer system across the US and China without any problems.
Yeah, we've been shipping Gen 4 modules for a good year, probably more now. We haven't had signal integrity problems.
Yeah, okay. Because, you know, I think that he is asking, you know, because you put the interposer, something like it, hot swap module is interposer, right? In between the host, the backplane, and the drive. So there should be some insertion loss there. So I asked if there is, you will do some signal boost, some signals to compensate for that insertion loss. I think that he's asking this question.
Yes, so we don't do that. And the reason that we don't do that is that the signal boosting would add a lot of additional factors. So it would add latency to the system. It would mean that you're not testing the original system because you have this extra active component in the way. And the other reason we don't do it is because our loss is not very significant. So our loss is around 4 dBs. The spec allows for around 40 dBs. So we would, in most systems, there is adequate margin to allow us to be in there.
Okay. A second question. He asked about the data pins.
So how would they be used? So during a hot plug test, for instance, so when the drive is plugged and functioning normally, all the switches are closed, everything is as transparent as we can possibly make it. During a pool operation, for instance, there's an FPGA on the board which does the very precise timing, and at the correctly specified points in time, the FPGA would order the switches to open. So the RF switches, for instance, would open and isolate the signal, so it would look exactly the same as if you removed the connector. The same with the power FETs. The power FETs would slew across and would open up and isolate the voltage rails.
Yeah. I think specifically there is a lot going in a power loss. There is a lot going on. So a few years ago, I had a very specific problem with a very well-known shipping motherboard, where we would pull power to a drive, and depending on whether the data lines were connected at the time of the power loss or disconnected, we could actually crash the root complex, the PCIe root complex on that motherboard. And this was a very complex issue, but the difference between a working system and a faulty system was that the data lines were connected at the point that we pulled power from the card. So there's a lot going on when you do a power up or a power down. So even though the power has been removed, the card still has interaction with the host in terms of SM bus, in terms of the data it has cached and its interactions. So even though there's no power to the system, it still makes a difference that the data lines are connected or not in some cases.
Which is why the Quarch module gives you this order of magnitude more testing than, for instance, just turning off the power to the drive would, because in that case you're only testing one scenario, not all of them.
Yes, thank you very much for your time.
Thank you very much.
Thank you to everyone for the questions as well and for your time. And if anything comes up, you have any questions after this, please get in touch with Saniffer or just send us a message directly and we'll be happy to help you.